Now we're going to look at systems of linear inequalities in two variables. The solution set of a system of linear inequalities is a set of points that satisfy all inequalities in the system. All inequalities are graphed on the same coordinate system or plane, and the overlap is the solutions of the system. It's also called the feasible region. The word feasible, base word feasible, that's usable, possible solutions. Alright, so now we're going to graph the following systems. And guys, in order to do or use what we learned in the last video, we just graph them one at a time. And I usually tell my students we're saving paper because we're going to put both of these on the same graph. So let me take the first one. And well, I need you to go ahead and graph the first one. Do you remember what you got to do? First, change it to an equation. Go get some points. So see if you can go get the intersection points and then graph them. So that's what I got. So if I graph it and then shade it, because this is everything that we've done, I'm going to shade those or graph those points, use a solid line, and then I'm going to figure out what side I need to shade. So I need you to go ahead and do that. Pause me and see if you end up with what I did here. I graph my points. I use the origin as a check. If I put my origin in, I do get a true statement, so that's why I shaded the origin side. So now, we're going to use the same graph, but we're going to, in a way, ignore what we've got on there. Go and graph the next one. Change it to an equation. Go get the points. And graph those. So I graphed the equation. If you'll notice, I'm ignoring this one. So I graphed these points. Now I've got to figure out, do I shade this side or do I shade this side? Now right now you need to start looking at where the overlap's going to be. If I shade the origin side, then it's going to be this little triangular section right in here. If I shade the other side, it'll be this other bigger piece. So let's go try the origin. That will give me a true statement. So I need to shade this whole side. So let's see what my picture looks like. The overlap. Notice the checkerboard effect right here. That is my solution. These are the points that will These are the points that will work in both of those inequalities at the same time. So in the back of the book, the answer that you will see, or the picture you will see, will just be the overlap. You will not see these other pieces. Okay? So that would be my solution. So it's similar to what we've done before. We're just saving graph paper. Now I need to look at this one. In this particular one, this is something that's going to pop up a lot. These are two special ones, and we need to know about these. First one, I've got x is greater than or equal to 0. If I have, or make this an equation, I'll have x equals 0. X equals 0 is a vertical line, which technically is your y-axis. So let me go get another line. And I'll put it on top of this one. I'll make it more solid so we can tell the difference here. Okay. Now if I shade, it says x is greater than or equal to 0. Well, I either shade this side or this side. Now the x values on this side are the values that are greater than or equal to 0. So I need to shade this side. So let me go get, this is a little pen thingy. I know you can do better on yours. I just thought that was cool. Okay. So I shaded those values where x is greater than or equal to 0. So now I'm going to ignore that one. Let's go get the next one. Y is greater than or equal to 0. Well, where y is equal to 0, that is my x-axis. So I need to go get that line. Let me make it a little bit solid, more solid. Now, for this one, I want my y values to be greater than 0. Well, where y values are positive is up here. Do you see the overlap? Let me go get my squiggle thing. My overlap is in here. And if you think about it, it's going to have a real good time. Whoopsie. This is my first quadrant. You got to ignore that part right there. So this is my first quadrant. This is my overlap. So whenever I see x and y greater than or equal to 0, I've got to know that they're looking, or they're considering just the points that are where my x's and my y's are both positive. So it's just this section right here. Okay. Now, a corner point of a feasible region is a point in the solution region that is the intersection of two boundary lines. So let's see what's happening on this one. They want us to graph the following systems of inequalities and find the coordinates of any corners. Now, if you'll notice right here, I've got x and y greater than or equal to 0. When I graph this first one, I not only, graph and shade it, but I also consider these two at the same time. So, go get your equation. And then go get the points that go with that and see if you end up with what I did. And I need you to go graph those. Now, if you'll notice, I did label my axes. Remember to label the equation you used, that you drew that boundary line with. Now, to shade. Remember, I'm looking at this one. I'm going to use the origin as a check. If I use the origin, it'll give me a true statement. So that means I need to shade the origin side. But at the same time, take this into consideration. So where all three of those overlap would be in this little triangle right here. Because I've got to stay in the first quadrant, I need to shade this side, so that would be this part right in here. I happen to have a nice little shading piece here. Let me move it over here. There. So this one, x and y greater than or equal to 0, you do them all at the same time. So now all I have left is this one right here. So, like before, let's go make it an equation. Okay. Go get points. And these aren't nice points. This one at least is not. And I'm going to show you something up here in just a second. So now go graph the points and connect them like you should. So I use little triangles. Now if you'll notice also, I indicate where these intersections are, my x and y intercepts, especially if they're not nice values, because I might have to use them. So I just make a little arrow and go, this is 23/3, okay, and this one is 23/4. Okay, now I still need to shade. Now what I shade can be this little sliver right in here, or this bigger portion. Well, let's go use the origin as a check. If I put the origin in, I get a true statement. So I need to shade to this side, so that means this bigger piece. So let's go get that little pencil again. See if I can do a little bit better. Not really. I do have some students that use a yellow highlighter for the first shade and then a blue for the second, and it comes out a real pretty green. But hopefully you get the idea here. Okay, now corners. It says list the corners that are attached to the feasible region. This is a corner. This is a corner, this is a corner, and this is a corner. A corner is made when you have two boundary lines that hit. So this is one corner right here. So that would be the 0, 23/3. This would be a corner. That would be 0, 0. This is a corner. That would be 4, 0. And then I have another corner. So let me move this down. See what all I've got. I usually get the ones that are on the axes. Now this one, that is to me up in the guts of the quadrant, well, this is why I ask you to list or indicate what your boundary lines are. And this is why we did what we did in the very first chapter. I've got two equations. They hit to form a point. So let me go. I could do the elimination method or substitution, or I can go to my matrix. Let's go edit. I'll have a 2 by 3, and I'll put them in. I've got 4, 3, and 23. I've got 2, 1, and 9. Second quit. Let me get the matrix back. See if I agree with it. And remember, I use that RREF, which is under math. For second matrix. Oh. So they hit at 2, 5. There's 2, 5, pretty close. So those are my corners. But the corners have to be attached to the feasible region. This one is not. If you'll notice, it's outside the feasible region, and this one is not either. So they have to be with the double shading. A feasible region is bounded if it is completely enclosed by the constraints, the linear inequalities that were used to form it. A feasible region is unbounded if it is not completely enclosed by the constraints. So the last two problems, this one right here, it is completely enclosed, so this is bounded. We had one a little bit earlier. This one is unbounded, and this one is unbounded. If you'll notice, this part right here, the shading will go to infinity, so it is not bounded. Okay? And I believe that's it for this particular video. Thank you.